Hello, this is Dr. Robert Faust with Faust BioAg Inc. I'm sitting here in my lab, and I was just thinking that I'd like to dispel a few misconceptions and educate our users on some of the facts about humic acid. For years, it's been sort of, even though there's been years and years of research done, there was always a kind of misconception. For most of the years I've been involved with it, scientists kept trying to find the answer, like what is the molecular formula of humic acid? And then only in the last few years, with the improved technologies, we have discovered that there's 800 different compounds within humic acid. So there's no specific compound called humic acid. It's really one of the few things in nature that's defined as a fraction. So you have humic acids with an S, really. And we've always known, I mean, they were always defined as a fraction going back, 60, 70, even I think around 100 years. Because you could take this humus, so-called humus, you could take a soil sample and you could start extracting. Well, so if you use an alkaline extraction method, you solubilize the so-called humic acids, and then you further fractionize them by acidifying that alkaline extract, or you just start out with an acid extract. So they define the alkaline soluble fraction as the humic acids, and that's usually black, and then the acid-soluble fraction was called the fulvic acid. There's no specific compound in nature called fulvic acid. It's actually a fraction of humic acids, and within humic acids with an S, 800 different chemical compounds have been determined, really, and in a range of functional groups. And we know which organic functional groups have the bioactivity and which ones actually have a negative effect or no effect. And it's really a color. It's about colors. The fractions are various colors, from black down to gray, brown, yellow, gold. And within fulvic acid, which is defined as the acid soluble, that seems to be the bioactive component. And it consists of what they call condensed tannins. That probably gets into another discussion. But the bioactivity is in the fulvic acid. We've done many tests using aeroponics in conjunction with universities, where we tested, humic, the full humics type product, which is a humate derived or leonardite derived solubilized material that would have all the humic fractions. And then we have used just the acid soluble fraction, the fulvic acid. And what it boils down to, when you have an aeroponic research system, you're not really working with soil or soil microbes, you're just putting an optimum package of molecules, of elements, and for plant growth, and then you see what difference soluble organic matter or species of carbon make, and that would be humic acids, fulvic acid, which is so we found that really in aeroponics and hydroponics, you only need the yellow fraction, so-called the fulvic fraction. And that makes sense because only the fulvic fraction is low molecular weight and can be taken up, can actually be utilized, can make it into the cells through the cell membranes. The black stuff can't. Matter of fact, the black fraction, or so-called humic acid fraction, not only can it's too high a molecular weight, it can't be absorbed by the plant roots directly. In fact, if you have a high concentration in the water, it can actually kind of glom on the plant roots and sort of plug them up, and then you'll see some negative effects. So It's complex. Humic acids are considered the most complex chemistry on Earth. So what I'm trying to get at here is the idea of solubility. Now, it's been thought that to be effective, the products have to be soluble. Okay, so let's say you take just raw humic acid and put it in a test tube with water. That's what happens. It's totally insoluble, and it's kind of hydrophobic too. I mean, it's hard to re-wet once it's dried. But this is pretty much what you get. That's water. That's just pure tap water. And that's the humic acid in the bottom, the raw humate from the mine, ground, powdered, whatever. Doesn't matter. It's not soluble. It's in its original state, which is bound together, a matrix of organic compounds derived from ancient organic matter and decomposition. And in some cases, compression like coal. So it's wound tight. The molecule is wrapped up just like a baseball has a center rubber core and then miles of string wrapped around that. Well, that's sort of what we're looking at here. And to get at that, you have to break it down so that the fractions come apart. That's what fractionization means. So from this black powder, which is derived from decomposition of organic matter, and it's just one stage is oxidized coal type material. It's not coal because it won't burn, but it's associated with coal. It's upper layers that are oxidized. So that's what you get. It's just clear water. Okay. So this is defined as the Fulvic fraction, Fulvic isolate, whatever you want to call it. It's defined as the low molecular weight, acid-soluble fraction of humic acid. So this is the only one that's acid-soluble. So bottom line, this is really the fraction that works, that does stuff, that plants can absorb directly. Actually cells, not just plants. I mean, it can be animals. It's just cells. It can be algae. Doesn't matter. It's a cellular response, and it makes it into the nucleus. And that's a whole other discussion, what happens. But anyway, so we have the yellow gold fraction, which is like our full power product. And that's where all the biological activity is. It's condensed tannins, and it contains active functional groups, aromatic functional groups. Again, that's a whole other subject of the biochemistry behind this. But the point of it is, this is a pH of 3.8. And so you'll see, if this also had the humic in it, you'd see that at the bottom, be a black blob at the bottom and yellow on top, because the so-called humic acids are only soluble in alkaline, not in acid. Fulvic acid is soluble in acid and alkali. This is where the bang is. This is what works in that matrix. Now, then we go to an activated product that's dissolved in water. So here's the unreacted from the mine. This is the reacted product, our humusol, or what we call full humics now. We call it full humics because it's got the full spectrum of humic acids. Now, it's not black like ink. It doesn't need to be black like ink. We could make it much more alkaline, and then the waxes, the very high molecular weight humic substances would solubilize, and then you'd have this. You'd have ink. So you have ink, okay? So that's a very, very high pH extract, like a pH of 11. But this one here, this is actually the bioactive fractions of humic acid are in this. and they're brown and yellow, and the black's just not going to work. It's just not absorbed. So if you took this product, which has got about a pH of 11.5, it's very typical of your liquid humic acids on the market today. And they call it the salts, the potassium salts of the humic acids. It's not humic acid anymore. It's pH of 11.5. It's highly alkaline. So technically it's salt. It's the salts of the humic acids, soluble salts. Okay, humic, fulvic, fulvic. Okay, now if I change the pH of this down to a more reasonable pH, I get this, the biologically active fraction. If I go completely acidic, I get this, the highly bioactive fraction. Now this, and if you do nothing, it's just nothing. It's going to happen. Okay. This one, if we change the pH of this, it's 11.5. So if I mix this with water, table water, it's a 6, 8, 7, something like that. It's gonna turn back into something like this. You see, it's all dependent on the pH. If you pour this, if you spray this on the soil, it's going to be the same situation is going to happen. It's just going to drop back into an insoluble form. So I realize that people don't seem to understand that the pH is what's responsible for whether this stuff is soluble or insoluble. But in terms of plant growth, it kind of doesn't matter. What matters is that it's been disintegrated by an activation process and oxidized. And that's what our full humic process does in a one-step process. And adding, it's certified, under OMRI as an organic input. And the rules of making this for organic use is that we use the minimum amount of hydroxides, of potassium hydroxide, to make it effective or soluble. Okay, that would mean we want to just make the biologically active component soluble. Because what's the point of adding excess alkalinity to it? Because as soon as you mix it with water or put it in the soil, it's going to go back to whatever the pH of that water or soil is. So look, people like it. There's a saying in the business, if it's black, they'll buy it. But it's not the black. The plant doesn't like the black. Let's just say the plant likes the yellow. So that's a tremendous misconception that it has to be inky color. You put it in water and it looks like ink. No, because as soon as you put that water with a pH of 11.5 into tap water or rainwater, it's going to revert back to the black stuff laying on the bottom. It's insoluble. So most soils are not a pH of 11. So most normal agricultural soils with a pH of anywhere between 5 and 8, is pretty much gonna, the black fraction or the fulvic or the humic fraction will just revert back to insoluble immediately when it's added to a soil, with a reasonable pH. Or if it's added to water, it's going to immediately go back. And that's why people have problems dissolving it, spraying it, and all that. And they don't realize that it's not really doing us any good. That's why we make a refined product. So if you want to mix this in water, yes, it won't revert back to insoluble. It stays soluble in acid or alkaline. And this is the biological activity. The black is not. Plants cannot utilize it. They can utilize some of the brown fraction because they can solubilize humic substances with enzymes and acids they produce in their roots. So if there's some particles of humic substance of the brown nature, sub-fulvic, let's say, plant roots themselves can solubilize it. But they can't really solubilize these black fractions. a lot of which actually contain wax. It's a part of humate or humic substances. Now we see my chart here. We see that that you can see this information, and it's going to tell you the colors. You go black, gray, brown, sort of brownish, goldish, and then pure yellow. They're your fractions. Maybe I can show this better if I put it here. And but this is crucial to understanding humic substances, because it's not really something that is simple. This is not simple. You have a range of molecular weights. See? Now, only the low molecular weights, say the brown down to the yellow, are really usable, are really going to affect plant growth or animal nutrition. The rest are way too high molecular weight to be absorbed. So they may add some carbon over time, but are resistant to decomposition, because these things are defined as the end product of the decomposition of organic matter. So they're decomposed as much as they can, and it's really like plant salts, cell salts, complex, very complex components, carbonyls, quinones, your carboxylics, phenyl carboxylics. Some of the top scientists that work in this field don't even like the term humic acid anymore. They think it should be called phenyl carboxylic acids. So what we originally thought, and what I originally learned back in the days before molecular genetics, and the days before advanced organic chemistry, we had a big misconception about humic acid. And I think the general public still does. And I think the biggest problem is when, they expect a black ink. And like I say, I ran into this in South America, where they have an expression in Spanish that translates as, if it's black, they'll buy it. Okay. But the thing of it is, yeah, it looks good. It's impressive. It looks like ink. But the plant's not going to take it up. It's not going to do anything. There's humic acids I've tested from China that they're very black like ink, very soluble. They're generally used as drilling mud, and that's to lubricate drill bits for oil and gas drilling and sealing up the well casing. But they don't have the biologically active. Yeah, it's humic acid, all right. They can sell this 80% humic acid, but it's not. It doesn't have the bioactive components. I learned this early on because I'd find stuff that was claimed to be only 35% humic acid, and it really gave some tremendous plant growth response. And I get some that's 80, 85%, and nothing. Either that or it had negative effects. So we were really in the infancy in those days. That'd be back in the 80s, 70s, and 80s. Well, this has advanced quite a bit to the point we know that all the bang, essentially, I mean, I know this is controversial, but it shouldn't be, because this is the bioactive component. This is the fraction that has the effects on cells, cellular effects, and it's a very popular product in hydroponics because it's immediately absorbed either through the leaf or the roots. The black stuff can't be absorbed through the leaf or the roots. It just sits there. It just interferes. It gets in the way. Now, if you put it in the soil, microbes eventually can pull it apart, and some of the gray and brown humics, the plant roots themselves, will solubilize into a lower molecular weight, like the fulvic. And then the microbes also benefit quite a bit from from some of these humic acids in the soil as an energy source, as a carbon source, and they can take it apart. But not much can take apart the black fraction. Matter of fact, we use it in potting mix. It doesn't really, it helps hold nutrients and maybe nitrogen, but it's just pretty much inert form of carbon, very stable form, just on the edge of coal, really. So we shouldn't get too concerned if a humic acid isn't soluble, the black kind, like the full humic, isn't always soluble in the water you put it in, because the water you put it in is going to be the wrong pH. So we tell people that try to dissolve it, add potassium hydroxide to the water, to the warm water that you use, and get it up to the pH where you will have solubility of all the fractions. And it will look like ink. But it won't stay there because you're adding hydrogen, and unless you kept it airtight container, the hydrogen ion being, the lightest element, is lost over time, and then the pH changes and it becomes less soluble. Okay, so you have to keep it airtight. But the point of it is, it's not really going to kind of matter, because if you put it in the water or the soil, it's going to revert. The solubility is just going to revert to whatever the pH of the soil is or the water. It's going to just turn back into black insoluble. Doesn't matter. The stuff that works is going to be soluble under all conditions, and that's contained within the full humic, or it's purified and concentrated within our full power product. So, I mean, even the completely insoluble stuff still has those components buried within its structure, a very tight, a very resistant structure. But given time, like over 3 or 4 months in the soil, even this becomes soluble and will affect plant growth in a positive way. The reason people want to solubilize it is because it makes it easier to mix it in a tank and spray it, or to run it through irrigation system. But it's if you're using soil application, it's much better to use our full humic granular and just apply it by broadcast or side dress. Like I say, we have to understand that this is not one substance. It's defined by as fractions. So I'm going to take a look at this and try to explain it of what we're really looking at here. So here's the chart of humic. This is what I was saying. The numbers at the bottom are molecular weights. So as it gets darker, the molecular weights go up. The fulvic acid is either yellow-brown or light yellow. I say golden, really. And the humic acids are dark brown and grayish, gray-black. Okay. The black fraction is called humin, Humin, and that has absolutely no plant growth effect at all. It's a stable substance that is part of the humic acid matrix, or the humate, leonardite, lignite, whatever you want to call it. So that's derived from lots of other things, even mudstone, shale, things like that. But the Humin is insoluble, pretty much insoluble, unless it's into a strong alkaline. It's not a beneficial substance. It doesn't matter. Humin is black. So it's kind of redundant, which is why we do what we do in making full power, which is just the light yellow, and how we solubilize a leonardite or humate product. And then ideally, when you dissolve it in water, you're going to get dark brown, gray, black. And hopefully the black stuff, it doesn't need to be in solution. You put enough hydroxide in there, and you create such a high pH as 11 and a half, that it starts to depolymerize some of the beneficial substances in the lower molecular weight product. So we want to avoid that. And so you have to understand the black isn't going to do anything. It can get in the way. It's not favorable. You can put it on the soil, fine. You know, it's an energy source for insects and earthworms and things like that in the soil. That can be a good thing. But don't expect any plant growth benefits from it. So I've had people that would say, oh, this product isn't dissolving very good. It's not all turning into ink. And, well, it doesn't need to. That's the point I'm trying to make. So if you got a nice brown color here, sort of brownish, reddish kind of color, that's our reacted full humic, where it's actually an activation process and it's controlled oxidation. So what you're getting there is just the humic acids. Yes, just the humic acids. Because the black, yes, it looks like ink, it looks nice, black's nice, but it's what they call the humin, H-U-M-I-N, which is not effective. It's not doing anything. And it can plug up stuff, too. I mean, it's sort of an insoluble material. It'll plug up spray tips and it settles in hoses. Like I say, you might get it soluble, and we do, at a pH of 11 and a half, but it's not going to stay soluble unless the water you put it in is 11 and a half, or the soil you put it on is 11 and a half, and that would be a disaster, because that's completely saline soil. It's probably not going to grow plants at all. Humic acid does help that situation, however. But if you put this black fraction, humin, you know, the high molecular weight, so it's not even called humic acid, it's called H-U-M-I-N. You put that on a soil that's acidic or even neutral, it's going to revert right back to insoluble. Fulvic won't, the yellow stuff won't, the brownish, goldish stuff there. The full humic is fine. At the bottom, you will see the H-U-M-I-N, humin, the insoluble fraction, is down there on the bottom. That's good, because if you made a liquid like this, you'd pour it off. You'd pour off the good stuff. The more biologically active, you'd pour that off. Oh, I got into the H-U-M-I-N, and I wasn't careful in my pouring, and so I ended up with, I poured the black stuff in there, turned it into ink. Now that's after letting it settle for a couple days. So, learn a little bit more about humic acid. It's crucial to life on Earth, and it has as many forms as, well, nature has a lot of diversity. And in what's contained within humic acid really depended on what it was derived from in the first place. And some of the more valuable materials that produce more biological activity is more of your hardwood trees, forests of hardwoods like oak. And in fact, that's what I'm saying, the yellow fractions, bioactive, is condensed tannins. And the tannins are derived from, you know, hardwood trees, like oaks. That's where you get tannins. So that's what counts. If it's from reed sedge or fresh or saltwater sedge or reeds, like some of the Leonardite products,
are from the eastern part of North Dakota. They are not, they're kind of disappointingly ineffective in many cases. And if you fractionize them, you'll find they have a very, very small amount of fulvic acid. You get very little out of that. So you have to choose your product source wisely, because it's not so simple as how much humic or fulvic acid has. So we have a label on our full power. It's the only approved test method. And we test for what they call the hydrophobic fraction, which is the fraction that has the biological activity. There are 5 fulvic acid fractions to make this even more complicated. So it's quite a bit to get to all that without destroying some of the very kind of delicate chemistry involved in this. Like I said, there's 800 different compounds. Some of them are stimulate cell division, some of them ATP transferase activity, all basic cellular functions. Some turn on things like plant resistance to pathogens, plants resistance to insects. That's what got me interested in this back in the 70s. We didn't know how or why. Now we know it's the tannins, of which there are several tannins. So it's very specific why and how it works, dependent on some complex chemistry. It's not simple. But keep in mind, it's not the black. The black, you may like the looks of that. That's not called humic acid. That's called HUMIN. Check it out on the chart here. Crucial to understanding humic acids. So thank you, and that's my little explanation of humic acid fractions and or why black's not always best.